Bismillahirrahmanirrahim. Hello everyone. I hope you have a great today. My name is Azmat Ali and I welcome you all in class of elementary number theory. In today's lecture we will start from question number 8a from the problems 1.1. The book that I am using here, the elementary number theory by David M. Burton. In last lecture we discussed up to question number 7. We start today from question number 8a. In question number 8a, the statement is verify that for all natural number n greater than or equal to 1 mean natural numbers, we have to prove this expression. So, I will use here mathematical induction. Suppose the given statement is denoted by P of n, that P of n is my statement. Then the first step that we call base step, we check the statement for n is equal to 1. The given statement for n is equal to 1 becomes the first number is 2 here on the left side, and if we put n is equal to 1 on the right side, we have 2 into 1 factorial over 1 factorial. This becomes 2 factorial. 2 factorial is 2 and 1 factorial is 1. 2 over 1 is 2. So the statement is true for n is equal to 1. Next, the second step is, this step is called inductive hypothesis. Inductive hypothesis. In this step, we suppose the given statement is true for n is equal to k. So this statement for n is equal to k becomes pk 2 into 6 into 10 into 14 up to so on 4k minus 2 is equal to 2k factorial over k factorial. Suppose this is expression 1. Next, we show that this is my step number 3. That is called inductive step. In this step, we show that the statement is also true for n is equal to k plus 1, the very next number, then k. Whenever the statement is true for n is equal to k. So the statement for n is equal to k plus 1 that we have to show is this becomes 2 into 6 into 10, 14 up to so on 4k minus 2. This is the kth number of this product, and what is the k plus 1th term of this product is given by just replacing n is equal to k plus 1 here. We have 4k plus 1 minus 2. This is 4k plus 4 minus 2, that is equal to 4k plus 2. This should be equal to, if we replace n is equal to k plus 1 on the right side, this becomes 2k plus 2 factorial over k plus 1 factorial. We will prove this statement is also true for n is equal to k plus 1. So, to prove this statement, I take the left side of this expression and replace this product is equal to 2k factorial over k factorial. Left hand side. Consider the left hand side. This is 2 into 6 into 10 into 14 up to so on 4k minus 2 into 4k plus 2. By using the truth of statement for n is equal to k and replacing this product is equal to 2k factorial over k factorial 4k plus 2 by using 1. by using 1. Next, we take common 2 from this. This becomes 2 into k plus 1, 2 into 2k plus 1 into 2k factorial over k factorial. If we see the right side of this statement, we have to complete the factorial of 2k plus 2. So to complete 2k plus 2 factorial, I divide this numerator and I multiply numerator and denominator by the term k plus 1. So by multiply k plus 1 with numerator and denominator both, k plus 1 into k factorial. Next, multiply 2 inside 2 with k plus 1. This gives us 2k plus 2 into 2k plus 1 into 2k factorial over k plus 1 into k factorial. Now, the numerator, this can be enclosed by the factorial 2k plus 2 factorial, and the denominator is simply k plus 1 factorial. That we have to prove, which is equal to right hand side. So next you write the given hence the statement is true for n is equal to k plus 1 whenever the statement is true for n is equal to k. Hence the statement is true for all positive integer by mathematical induction. Next we discuss its b part, that is very important. Okay, next we discuss its b part. This is very interesting. The statement is, question says, use part A to obtain the inequality. This inequality 2 raised to power n into n factorial square less than or equal to 2n factorial. You can solve this part again by using mathematical induction, but I think it will lose the beauty of mathematics. It would be like as solving two separate problems. So I will solve this part by using its first part with the algebraic manipulation or logical reasoning without repeating the whole process of induction. So if we consider in the first part, this product is equal to 2n factorial over n factorial. If we multiply n factorial on both sides, we have, you will write from the first part of question number 8, we can write n factorial into 2 into 6 into 10 into 14 up to so on 4n minus 2 is equal to 2n whole factorial. This inequality that we have to prove further can be written as this is equal to 1 less than or equal to, if we divide this number the left hand side on both sides, this gives us 2n factorial over 2 raised to power n into n factorial whole square. It means we will prove 2n factorial over 2 raised to power n into n factorial square is greater than or equal to 1 for all n greater than or equal to 1. So suppose this is my question number 1. Now from this equation, firstly we consider this product. Consider the product 2 into 6 into 10 into 14 up to so on 4 minus 2. If we write it as in form of product, this can be written as k is equal to 1 to n 4k minus 2. This is the closed form of this expansion. If we take 2 as a common from this bracket, this can be written as k is equal to 1 to n 2 into 2k minus 1. By applying product n time on this number 2 and shifting this number outside the product, this can be written as 2 whole power n, k is equal to 1 to n 2k minus 1. So substituting this whole product in 1 becomes 2n factorial is equal to n factorial into 2 raised to power n, and product of k is equal to 1 to n 2k minus 1. Dividing on both sides by these two numbers, this gives us 2n whole factorial over n factorial into 2 raised to power n is equal to k is equal to 1 to n 2k minus 1. To form the left side of this inequality, we multiply the denominator by n factorial on both sides, or dividing both sides by n factorial. This gives us 2n factorial over n factorial whole square into 2 raised to power n is equal to product n is equal to k is equal to 1 to n 2k minus 1 over n factorial. We have to show that this side is greater than or equal to 1. This would be greater than or equal to 1 if and only if this is greater than or equal to 1. We write 2n whole factorial over n factorial square into 2 raised to power n is greater than or equal to 1 if this term product k is equal to 1 to n 2k minus 1 over n factorial is greater than or equal to 1. So now our target is to show that this term is greater than or equal to 1. That consequently show that our inequality. So if we compare this term 2k minus 1 with k as 2k minus 1 and k for all k greater than or equal to 1, which side is bigger? When you put k is equal to 1 here, this becomes 1 and this is also 1. But if we take k is equal to 2 here, this gives us 3 and this is 2. For k is equal to 3, this gives us 5 and this is 3. It means this left side is always greater than the right side. Only when k is equal to 1, they are equal. So this term is greater than or equal to k. Now by taking product on both sides up to n terms, this gives us k is equal to 1 to n 2k minus 1 is greater than or equal to product of these terms. Next, if you open this product, this is equal to 1 into 2 into 3 into 4 up to so on n. What is this? This is n factorial simply. It means this is equal to n factorial. Dividing n factorial on both sides, k is equal to 1 to n 2k minus 1 over n factorial. This is greater than or equal to 1. That we have to prove. And this shows that our inequality. So in today's lecture we have discussed question number 8 properly. I hope now you have a clear understanding of this question. Inshallah, in the next lecture we will start from question number 9. If you find my videos are helpful for you, kindly like, share and subscribe my channel. Okay, take care. See you in the next lecture. Allah Hafiz.